Hello, I will summarize my project, including motivation, methodology, and findings. The title of my project is Non-Adaptive Group Testing, Algorithm Simulation and Performance Comparison, and my project supervisor is Dr. Siddhas Jagai. We begin the project with an overview of group testing. The group testing is performed on a large set N with a total of N atoms, and the subset D of N is called the set of defective atoms, of which there are a total of D atoms. The goal of the group testing is to accurately identify the defective atoms in your group testing using algorithms. And much of the work has been carried out previously in group testing. Many decoding algorithms for group testing have been proposed. Studies have been conducted on how to reduce false outputs in group testing, and therefore group testing is proposed. In addition, existing research has analyzed how the parameters in various algorithms can be selected to achieve optimum performance. However, there are areas of existing research that are still lacking. No other strategies used, no comparison between algorithms, and no investigation of the relationship between T and ND. Therefore, the motivation for this project is to contribute to society and to the development of group testing on the one hand, and to fill the gap in previous research on the other hand. My project focuses on non-adaptive group testing, and we classify the study strategies into three categories: P, G, and near-constant strategies. Afterwards, we compare the two types of algorithms, noiseless and noisy, with the three strategies for simulation. Next, I will illustrate for the algorithms and start with the noiseless situation. CM algorithm is mainly a column matching process. The resulting vector is compared with the column vector, representing each atom in the matrix, and if all the positions with the column vector of 1 also have a result output of 1, then the atom is defective. To illustrate, the fifth column of the M matrix shown below is not a defective atom. We can see this is 0. But the result of each test it is involved in is positive. We can see this. So it ends up being a defective atom. The D algorithm is very similar to the CM algorithm. The difference being that an atom is defective if only that atom is set to 1 in a row of the matrix and the result output is 1. The CC algorithm is based on the coupon collection problem and differs from the CM and DD algorithms in that it is a row processing process. The idea being to exclude atoms that are placed at 1 in rows with a result of 0. The remaining atoms after all rows have been retrieved are both defective. And we can see this. The result vector is 0, and we exclude this atom, this atom, this atom, this. So finally, we remain this atom is defective. And we use this formula to find the optimum t-value. The left-hand side of the formula indicates the number of atoms selected in a test with a negative result, and the right-hand side of the formula shows the number of times the coupon collection question is taken. And the LP algorithm differs from all of the algorithms above in that it replaces the output 0 and 1 integers with any real number greater than or equal to 0. The value of each atom output is Zi, and the exact value of Zi is bounded by the following rules. And we take the approach of identifying atoms as non-defective when Zi equal to 0, and atoms as defective when Zi greater than 0. Next, we will discuss the noisy algorithms. The noisy CM, DD, and LP algorithms do not change the recognition principle compared to the noiseless algorithms, except that noisy levels are added to the noisy algorithms. We can see this. This is noisy level 5. And the parameters unique to each algorithm are used to identify defective atoms. For example, delta, Y1, Y2, omega, and tau. And there are two more special algorithms in the noisy situation: the separate algorithm and belief propagation. The separate algorithm mainly uses knowledge related to information theory, using conditional probability and entropy for identification, And we use this formula to identify defective atoms, and this is the conditional probability of this. For belief propagation, we set up two kinds of message, one that from the atoms to the test, and another that from the test to the atoms. The overall process is similar to the transmission of optical fibers. This, maybe this, this. A message iteration is complete when the values of all the atom nodes and test nodes message do not change in a single transmission. We calculate the information value of each atom node according to the following formula. Here are the results of the project simulations. This is P strategy in noiseless simulation, G strategy, and near constant strategy. It can be found that among all the strategies, the CM and CC algorithms are similar in efficiency, and that the DD and LP algorithms are similar in efficiency. These two. The near constant strategy algorithm performed the best compared to the other two strategies, requiring fewer tests to achieve 99% recognition accuracy. And we also found that the LP algorithm performed the best under the P strategy and the near constant strategy. And the DD algorithm performed slightly better than the LP algorithm under the G strategy. You can see this. And below are the simulation results of the noisy algorithms. It can be seen that this is G, this is near constant, and we found that the noisy algorithms under the near constant strategy is the fastest at identifying defective atoms, and all the noisy algorithms perform slightly better compared to the other strategies. For other strategies, the noisy LP algorithms performs most constantly under the P strategy. And the noisy CM algorithm's performance is highly susceptible to the p-value. And unlike the other algorithms, noisy LP performs the worst under the G strategy compared to itself. The belief propagation and noisy DD algorithm perform well under all strategies, and there is a huge gap between them and the noisy CM and separate algorithm, the orange and red line, and the green and purple line. As for the relationship between T and D, we found that the larger the number of defective atoms, the less efficient the algorithm is, and the more costly it is to identify defective atoms. As for the relationship between T and N, we found that when the value of N is large enough, in this case, N is greater than 200, the T required to achieve 99% recognition success rate does not increase as N increases, but smoothly within a certain range. Thus, the relationship between T and N is not a positive feedback relationship all the time, but in stages. And we still have some limitations in this project. The first is the limitations of the computer hardware configuration. Due to the CPU's limited power, we didn't set NID to particular large values. And the second limitation is that all algorithms in this paper are texted based on Bernoulli design, and there is no output such as weak positive and weak negative. In the future, we will compare algorithms against each other for adaptive group testing. Secondly, we are going to vary these values and observe the performance of the algorithms under other parameter settings. And thank you for listening. This is my project summary. Thank you.